recordings, the Zoom recordings don't seem to be working well, but the other ones, the normal lecture capture is working. All right, so that's for your reference material. All right, guys, we move on to today's lecture now. Today we will be looking at see if this is power. Okay, I'm just powering it up now. We will be looking at two's complement. We continue with two's complement today. All right? Okay, we continue with two's complement. Okay. Let me switch over to the document camera. Lights. All right, we have lights. Okay. We converted a number. We converted a number to two's complement. Now, when we did that example was deliberately done yesterday to show that a two's complement conversion from binary to two's complement is not straightforward. There is a set of rules to be observed. By the way, is the Wednesday group, today is Wednesday, right? Is the Wednesday group already done their tutorial, or is it later on this afternoon? What time is that? Oh, 5. Wednesday is 5 o'clock. Okay, all right. Okay, please ensure that you attend your respective tutorial groups. Otherwise, attendance will not be accepted, all right? You'll write your name on that sheet of paper, but it may not mean that we'll record your attendance, okay, on the system. Okay, all right. So, the questions which I asked you yesterday, hey, is this a positive number or negative number? Because, you know, we started off with a bit pattern. We don't know whether it's positive or negative. Because remember, in two's complement, there is a different bit pattern for positive numbers. There's a different sequence to do positive numbers. And there is a different sequence to negative numbers. So therefore, the same applies for going from decimal to two's complement. There are two pathways. Positive is a different pathway, natural binary pathway. Negative, we have to follow those steps. The same goes for going from two's complement, going backwards from two's complement, going backwards to binary. If it's positive, it's got to apply a different pathway, and a negative, it's got to apply a different pathway. So when we did example one was flawed, right? Example 1 was flawed, right? Not enough info, right? Not enough info. All right. So let's have a look at how to do conversion. Today's date is, does anyone have the date? 6th, all right. 6th April 2022, and this is week 3, lecture 2, right? Is that lecture 2? Yeah, lecture 2, all right. 6th April, week 3, lecture 2. All right. So the steps, guys, the steps. The steps is, number 1, two's comp to decimal. Number 1, it's all about the number of bits. The number of bits required for natural binary to 2's comp have to be, for decimal to 2's comp have to be determined. And I'll focus on number one later. All right. I think I mentioned this to you. Remember when, I don't know if you wrote it down in your exercise book yesterday. I said, hey, let's have a look at some example which we were doing. I said, can we do this problem in 4 bits? And you said no. Remember we did that problem in 2's complement problem. And we said no, we couldn't do it. And the reason why we couldn't do it was because, the reason we couldn't do it is because there was not enough bits available. All right. Now, all right. Always look at the most significant bit. All right. If MSB is equal to 0, then positive number. If MSB is equal to 1, then it is a negative number. All right? Okay. If it is a positive number, then convert to decimal like natural binary. If it is a negative number, then apply further steps which are in reverse. You can note it down, which are in reverse of what we did earlier on. All right, let's relook at example 1. Let's relook at example 1. 0, 1, 1, 0. And it says, and you say that, hey, this system is based in 2's complement. All right. Because this is 0, that means it's a positive number. Therefore, 0, 1, 1, 0, 0, 1, 1, 0 is 0, 1, 1, 0 is positive 6. Okay. Now, I want you to make another note there, that almost always, whenever we are dealing with positive numbers, it's always going to be in natural binary. Positive numbers is always related to natural binary. All right. Positive numbers always related to natural binary. So I'm not going to write everything down. I'm just telling you, and you guys can note that up. All right. Positive numbers is always related to natural binary. All right. Now let's have a look at another one. Yeah.
So it's like room number is it?
019-101. Okay. All right. So this is positive, just to ensure what it was. All right. Now let's have a look at some more examples. All right. Now what's the step? Let's look at example 2. Okay, the steps here. What are the steps? Let me just give you the steps. Step 1 is if MSB is equal to 1, then it is number is negative. Step 2, you've got to flip the bits. Step 3, you add 1. Step 4, convert to decimal. All right. Okay, let's have a look at another example. Example 2. Let's look at example 2. All right. Okay. Let's look at the number 1000101. Okay. And we've got to convert that into, and somebody tells you it's 2's complement. Now, the first thing we identify is that is our MSB is equal to 1, which means that it's a negative number. Right? In sign and magnitude, we would have only gone and considered the remaining bits. But in this case here, what we are doing is we are taking our 1 and then we are looking at the other bits. Okay. So now, what's the next step? So the number was given, what is it? 1000101. We've got to flip, which is also known as 1's complement. Actually, not 1's complement, just flip, right? Then we add 1. Zero plus 1 is 1, 1, 0, 0, 111. All right? So we flipped the bit, we've added 1. So we have 0, 111, 0, 11, base 2, which is equal to what? Let's now convert that to decimal. That's 1, 2, 4, 8, 16, 32. So we have 1 plus 2 plus 8 is 10, 26, 30, 27, plus 32, 39. What did you guys get? 49? 49? And remember, the number was negative. 50? Okay, 59. And remember, the number was negative. Okay, where did we get that negative from? Because MSB was equal to 1. Right, the most significant bit is equal to 1. All right. Let's look at another example, example 3. Now, can you tell me in this example, what was deficient in this example? I've given you this example, example 2. What was deficient?
The bit system was not specified.
Well, I did say the system. You said the word system. The system is 2's complement. The number of bits. Yeah, that's what you meant, right? You have to use the correct terminology to mean the right thing. I knew straight away what he was meaning. He probably meant number of bits. But he said system. The system is 2's complement, right? So just note over here, number of bits is missing. Now, example 3, redo example 2, but consider 8-bit system. I'm going to give you 2 minutes to do it very quickly. Simple as this one. This time around, it's really easy. Guys, when we, yeah? Yeah. All right, straight away. You can just look at it. Oh, no, it won't be positive 59. The bit pattern has changed. We've done flipping and all that kind of thing. The 59 came from when we did flipping, then added 1. Go to example 2. Right? Look at how many bits we've used. It's 1000101. So there'll be 0, 1, 000101. Right? And what does that number mean now? Can you get that number up? Two, 4, 1, 2, 4, 8, 16, 32, 64. What do you get? Why are you laughing? There's something funny. All right. You like that number, eh? Yes. All right. Okay. Okay. All right. 69. Can you see? By changing the number of bits, we didn't change the pattern. We just changed the number of bits. And remember, technically speaking, remember when we used to say if you add padding, if you add zeros before the number, it shouldn't change. So 007 or 0007 is still the number 7. But in this case, by changing, adding extra bits in 2's complement, the whole number is changed. Right? So make these subtle notes underneath the thing. Some things I again repeat. Certain things I'm just saying, I'm not writing everything down. I'm only writing the calculations down. All right? The rest of it, I'm expecting you to note down, jot down, or whatever. Okay. Let's look at this one now. Let's now do 1 1 1 0 0 1 in 8 bits. So, firstly, what do we notice, guys? We notice that the most significant bit is 1. Therefore, this is a negative number. All right? So, the steps. We take our given number, which was given bit pattern, which is 1111, 0001. And remember, it's 8 bits. Yeah? Okay? Then we flip. That becomes 4 zeros, 1110. Then we add 1. 0 plus 1 is 1. And 4 zeros and 4 ones is equals to 15. But our 4 1 0001 in 2's complement, that's 2, in 2's complement is equals to negative 15. Where does the negative number come from? It comes from there. That's our answer. Answer is negative 15. Okay? Now, as homework, what if example 4 was 10 bits? Homework. Do this on your, yeah? I think you guys have got an idea. Now, there was another point I wanted to demonstrate. This is in regards to, see, I made 2 notes over here. I made 2 notes. Number 1, number 2. Number 2 was the procedure. Number 2 was the procedure, right? We went through that way. But number 2 was the procedure. Yeah, remember this? We just wrote this down. Number 1, I said number of bits required. Number of bits required. Okay. So, I want to show you with regards to note number 1. Maybe I shouldn't have written it there, I should just separately. All right. Okay. With regards to note 1 earlier. All right. Okay. Consider this is not from going from binary to decimal. This is going from decimal to binary. Consider the number negative 28. And I want you to solve it, attempt to solve it in 4-bit, in 4-bit, 5-bit, and 6-bit. Attempt to convert to 2's comp in 4-bit, 5-bit, and 6-bit. All right. So let's pull some lines. 4-bit, 5-bit, and 6-bit. And I want you to see the evolution. All right, negative 28, obviously, the absolute value of negative 28 is equal to 28. We already know this. And negative 28 will equal to, in natural binary, what will that equal to, guys? Anyone remember? Anyone memorize the table? What do you have? Triple one, double zero? All right. Now already in the 4-bit situation, let me write the answer in black. So this is some side working. This is our table top. We have 111, 00 in base 2. We can't proceed in any event because you've already got an overflow. So we cannot proceed. We cannot proceed because it's already an overflow, right? If we were to proceed with the flipping and all that, what would happen? We'd do a 0. We've got to flip, make it 0, 0, 1, 1, and then add a 1, so it'll become 0, 1, 00, and it'll give you a positive answer. Right? So if we proceed, this would have become 1, 1, 0, 0, we flip, it will become 0, 0, 1, 1, we add 1, that will become 0, 1, 00, and 0, 1, 00 is equal to the number 4. Therefore, the answer becomes negative 4, which is totally out of whack. Right? Do you see? Because it's starts with a 0, it's totally out of whack. Negative 28, negative 28. Okay, let's look at 5-bit. Let's look at 5-bit. So 5-bit, we start off with 111, 00. Okay, let's start off. So we are given 111, 00. We flip because it is a negative number, right? We want to convert it to a negative number. We add a 1, right? We add a 1, and then once again we end up with this. So our answer is once again 00. Our answer becomes 00, 1, 00. And because the most significant bit is 0, because the most significant bit is 0, that means it's positive. Therefore, that is referring to some answer near number 4. Okay, let's look at 6-bit. In 6-bit, that same bit pattern, it was given 111, 00. In 6-bit, that becomes 0, 111, 00, right? That's in 6-bit. That's in 6-bit, right? Over here, that was in 4 bits. So our given was 111, 00, right? Okay. Now, what do? We now flip the bits. We flip. There'll be 1, 000, 11. We add 1, 0, 0, 100. Hey, that's starting to look good now. So our answer in this case, so possible answer, we should write possible answer, is 100, 100. Now, that is MSB is equal to 1, therefore it is a negative number. So let's now convert it back and see if we get negative. What was our target? Negative 28. So 100, 100, right? We're going to flip. Right? 011, 011. we add 1 plus 1. We get 1 plus 0, 1 is 0, that 0, get that, 0, 1, 1. What do we get, guys? Again, we get a positive number. All right. So over here, you have a situation. You have a situation where you've got to consider. You've got to consider 0 carry 1. Sorry? It's correct. Yeah. Okay. You've got to consider that the number of bits, so my point over here is, as because we were referring to note number 1, the number of bits plays a very crucial role in 2's complement. If you have the wrong number of bits, it'll give you the wrong answer. So that is my emphasis point here. Okay. Let us now look at some math operations. So we moved on to another topic now. So for 2's complement, we've looked at going from decimal to binary. We've looked at binary to decimal, and we've looked at the cases where 2's complement sometimes does not work. What was the principle behind 2's complement? Why did we get into all these 2's complement and all that? Why? Well, because none of the other systems were allowing subtraction, addition and subtraction properly. But 2's complement is the best available system, right? Not probably the perfect system, but it's the best available system provided you work within a particular range of bits, right? You work within the same, an allowable number of bits. All right, let's look at some math operations. All right, number 1, we've done addition, done, right? We did binary addition. Number 2, we've done subtraction, right? Number 3. Now let's consider these two. Shifting bits to the left. Number 4, shifting bits to the right. All right. Okay, let's do number 3. Okay. Example 1. So these are some other, like usually when we deal with decimal, we only know addition, subtraction, and then based on addition, if you do repeated addition, you get multiplication, and if you do repeated subtraction, you get division, right? And from there you build onwards. Okay. Now, in this case here, in binary, you can play with bits. You can flip bits, like what we did, flipping of bits. We've done addition of binary. We've done subtraction, which is based on 2's complement. Right, that's the best system. Let's now look at the number 7. Let's consider the number 7. 7, let's put it in 4 bits, 0, 1, 1, 1. Now, if I load a 0 from the left-hand side, if I load a 0 from the left-hand side, that becomes 111, 0. Now, can you convert 111, 0 for me? What is that? What number is that in natural binary? 14. Let's look at example 2. Let's look at a bigger number. Let's look at the number 11. 11 would be 1011, right? And let's do 5 bits. Okay. right? And we load a 0. Right? If you load a 0, that becomes that 1 will come here. That padding 0 will fall off. Right? 1 0 1 1 0. What does that mean, guys? What is 1 0 1 1 0? Can you guys convert that quickly? $22. Now, from your intuition, from these two examples, using your intuition, what does shifting or loading a 0 to the left mean? When you shift, obviously you've got to shift it with a 0, right? Doubles the number. Yes. Okay. So now you have figured that shifting by 1 bit to the left is multiply by 2, or yeah, right? And of course, we've got to do it by loading a 0 in the LSB. All right, we load a 0 to the LSB, but everything is moved. Okay. Guys, now it's homework. Not homework. Let's consider what happens if you shift by n, letter n bits to the left. So let us consider the number 8. Oh no, let's consider the number 3. 3, that's in 6 bits. Let's do one shift. Shift 0, 1 shift. That will become 0 0 0 1 1 0, which is same as 6. Let's do 2 shifts. That will become 0 0 1 1 0 0, which is 1 1 0 0. That's 12. So what is happening here, guys? So when you've done 1 bit shift, okay, 1 bit shift, it is same as multiplied by 2. 2 bit shift multiplied by 4. N bit shift is multiplied by 2 to the power of n, which is this multiplied by 2 to the power of 1, multiplied by 2 to the power of 2. Yeah? You've got to think along the lines of powers. We're always doing in powers, bases and powers. All right? Okay. All right. Now, shift bits to the right. Okay? Shift bits to the right. Okay, let's apply those same examples. What numbers did we choose early on, guys? We said 7, yeah? 7 is same as 0 triple 1. Now, if I load a 0, this way, right? And let us restrict it to 4 bits. Yeah? Let us stick the system to 4 bits. Right? if I load a 0 and I restrict the system to 4 bits, so this will become 0, 0, 1, 1, which is 3. Now, somebody would have asked me, hey, what if I had a 5-bit system and I load a 0? Well, all that 0 does is it becomes padding, yeah, because it was already a 4-bit number. Okay, so the play is in when you have a restricted number of bits. Okay, let's look at example 2. Let's look at the number 22. 22. We just did this a while ago. 22 is 1, 0, 1, 1, 0. Okay? And we load zero that way. And let's say this time around, we restrict it to 5 bits. So that becomes a 0, 1, 0, 1, 1. That is what? 11. Now example 3. So you're starting to see a pattern now. It's doing divide by 2. But hey, we had an odd number here. 7 divided by 2 is actually 3.5, but it gave us an answer of 3. And 22 divided by 2 is perfect 11. It gives us the right answer. Let's do another one. Let's try the number 15. Right? And then when we load a 0, we shift with 0 to the 0 from the MSB. Right? We get 0, 111, which is a 7. So what we learn from here is that what we observe is that shifting right shift to the right is the same as divide by 2. Shift to the right is divide by 2. For an even number. Right, for an even number. That is a very important point here. For an even number, it is divide by 2. Shift to the right is for an odd number is what happens? What happens? Odd number. Okay, number 1. The first thing which happens is, if you have a look, for an odd number, that most significant bit, this 1 over here and this 1 over here, in the 2 odd numbers, example 1 and example 3, the 2 least significant bit was 1. Right? LSB in odd numbers is equal to 1. What happens? LSB falls off. Yeah? Have you noticed in LSB in odd numbers is equal to 1, and you could say even numbers LSB is equal to 0. Yeah, you could say that. For even numbers LSB is equal to 0. Now LSB falls off, so therefore shift to the right results in what do you say, divide by 2 and then round down. That's the thing, divide by 2 and round down, right? Right? Because odd numbers are not divisible by 2. So obviously there will be a remainder, there will be a 0.5, and it gets rounded down. All right, guys. So that brings us to an end. There is lots of other things. Some other homework which I would like you to check out. Some other homework which I would like you to check out is there are some other operations. For example, binary multiplication. Some other formatting methods such as ASCII, and look at the notes on the Moodle, eh? Notes on Moodle. So over here in my lectures, I'm more focusing on the examples, right? Not so much writing notes, right? I want to focus more on the examples and talk to you and explain things so that you have a grasp of what we're doing. Now let us now move to, so we will now put a stop over there. Otherwise, we can go for another 7 weeks doing just number systems. There's many number systems which we can go into IEEE, we can go to an IBM. Within IBM, there's a version 1, version 2, version 3. IEEE, there's so many versions. There's lots and lots of different things which you can do. But we've got to pull a line because remember, we want to head towards hardware. So we can't be just talking about numbers and not talk, you know, and then expect to finish hardware. We will now move to another topic which is called Boolean operations. New topic. Right? Okay, so this is where your hardware starts. This is where your hardware begins, all right? Okay, a lot of things we are writing on paper, but I want you to visualize, I would like you to visualize those particular circuits or whatever numbers we are talking about, whatever we are writing in theory, and this is like mathematical, but this is Boolean mathematical, right? Boolean means, the word Boolean means either a 1 or a 0, right? The word bool means either a 1 or a 0. Binary logic, right? Binary logic. All right, now, when I say logic 1, I want you to think of things in hardware. Everything which we write down has got an equivalent hardware representation. So when I say logic 1, it means positive 5. When I say logic 0, it means 0 volts, positive 5 volts and 0 volts, right? Okay, so let us start off with the first gate. We have the first gate known as the NOT gate, or sometimes known as the inverter, right? Guys, did you, for those of you who did computer science, did you cover gates in ME161? All right, good. Okay. All right, so let's have a look at this gate, guys. Now, this is the circuit symbol. I'm showing you the circuit symbol, but in reality, it is a chip. In reality, it is a chip, or you can build it using some circuitry. You can use it, if you're doing 212, how many of you guys are doing 212? Right, if you're doing 212, you probably hit, BJ, you've already starting to go into bipolar junction transistors already, or not yet? Okay, you can use transistors to build this gate. This gate, this is the circuit symbol which we are drawing on paper or on software. But in reality, there is a parallel world where you represent that physically, right? Like I can draw a light bulb, but in reality, you have a physical light bulb in the ceiling, all right? Okay, so the way this thing works is, and I'm going to introduce you to some concepts over here, is that this is your input, that is your output, okay? Now, there's something known as a truth table, right? Okay, a truth table. A truth table makes you tell the truth. Okay. You have inputs on one side and output on one side. All right. Now, how many inputs do we have? No. we have one input and one output. Look at the diagram. Simple system. Single input, single output. You can write that down, but later on, because you'll get so used to it, it won't be necessary. Single input, single output. Now, because we've got single input, and remember, we're using Boolean circuitry. So Boolean, what are the possible combinations in Boolean in terms of digits? Boolean is what? Referring to which base? Base 2, right? There's only two possible. You can either have bit 0 or 1 bit. 0 bit or 1 bit. So two possible combinations. So even though you've got one input, there are two possible combinations. Either you can feed a 0 in there, or you can feed a 1 in there. Yeah? Okay, you understand what I'm saying? You can either feed a 0 in there or a 1 in there. So if we feed a 0, so this is the left hand side is our input side of the table. You can label that in pencil or something. That's our input side of the table. And the output side, look at the name. Look at the name. It is an inverter. It is an inverter. So it's flipping, yeah. Inverter, flipper, right? So that becomes a 1, 0 becomes a 1, and 1 becomes a 0, right? So it's flipping the bit. So this is where you start to think, hey, we were doing some flipping early on when we were doing 2's complement. So in hardware, the implementation is done using this, using a NOT gate. Anything to do with flipping of bits, right, is done using that. So let me give you an example in actual thing, right? So you would like a sensor. Let's say the sensor gives an output of 1, right? A sensor. Listen to this carefully. I want you to think of things in terms of hardware. It's not good for you to think of things only in terms of paper. It has to be in hardware. If you have a sensor, light sensor, right? A light sensor. It gives an output of 1 when the light shines on it. Output of 1 when the light shines on it. It gives output of 0 when it is dark. If you connect it directly to a light bulb, when will the light on? Yeah. So the light will on when the sun shines or when it's during the light, right? So when in the daytime, the sun is shining or there's a lot of light in the atmosphere, the sensor will give an output of 1 and the LED will come on, right? And during the night, the LED will turn off. But that doesn't make any sense. Doesn't serve any purpose. Because you want the light to turn on, as the engineer, as the designer, you want the light to turn on during the evening and turn off during the day. So what are you going to do? You put your sensor, connect it to an inverter, right? Your sensor comes here, connect it to an inverter, and your LED comes here, right? Okay, your LED is light emitting diode, right? Okay, so in the daytime, when the light shines on it, the sensor gives an output of 1. The inverter flips that 1 to what? 0. So the LED will stay off. In the nighttime, it's dark. The sensor gives an output of 0. The inverter flips that 0 to 1, and the LED turns on. So you have to think of things along practical lines. All right, guys? Okay. Let me just show you one more line before we finish off this afternoon. Okay, so the Boolean, that is the truth table. So that is the circuit diagram. This is the truth table. All right? Now, the Boolean algebra is written as such, the mathematical way to write it. Ax is equals to A bar or A prime. Right? And we did this early on. Logic 0 is same as 0 volts. Sometimes people call it low, capital L-O-W, capital L, capital O, capital W. And sometimes it is -3, -5 volts, -12 volts, 0 volts. Logic 1 is sometimes as +5 volts commonly. People call it high, +3 volts.